to the storm. It's coming.
I've heard.
Have you seen that?
Okay, so here we finally have the box that I wanted to start with. So actually this is a review slide, and in order to successfully work gases, you need to kind of think of them as being gases, completely filling their container, being compressible, and all that. So what I like to do is to draw a box like this, and these little particles are my gas particles, and they're bouncing against the side of their container, creating a pressure. Remember, pressure is force per given area. So when we talk, I think we'll get to it today, we ultimately need to describe the pressure of those gas particles banging against their container, the temperature at which those gas particles are moving around, the volume that's containing those gas particles, and the number of moles of gas particles that are in there. So one of the things that we don't need to do is identity. Okay, so in other words, like if you have nitrogen gas, it will behave the same as carbon dioxide gas, will behave the same as water vapor. Okay, so the identity of the gas does not matter as long as it's behaving what we say ideally. Okay, so those 4 things. And we spent some time looking at kind of how a few of these variables relate to each other. So for instance, I know we talked about these 2. We said that if you increase the temperature, okay, and you don't make the box any bigger, your pressure is going to increase. Okay, I'm pretty sure we talked about these 2 also. So you can kind of isolate them in pairs, and that's what we're going to do again today. We said that, for instance, if your balloon is cool, okay, but then your balloon heats up, it gets taunter. So let's see, no, I said that wrong. That would be that would be the pressure and the temperature. See, temperature and volume. Okay, I don't know if we talked about that. I know we talked about these 2. Okay, if you're blowing up a balloon, okay, you are increasing the number of moles of gas particles in there, and the volume will increase to a certain extent until you reach the end of the latex being able to handle that volume. Okay, so those are those. We need to take one more quick look at temperature. So one of the 4 things in order to describe what a gas is you've got to say what its temperature is. And temperature is not the same thing as heat content, and I think we talked about that. Temperature and thermal energy are different. But temperature will tell you what direction energy will flow, and energy always flows from the hotter object to the cooler object. But the thing we need to focus on with regard to gases is that temperature term, that temperature that you're describing your gas at, needs to be on the temperature scale that, frankly, I don't use much in everyday life when I look at the temperature of the air outside. It's the Kelvin temperature scale. And I've got some slides to kind of show you why that's going to be. But the thing about the Kelvin temperature scale is it has this important point on the temperature scale called absolute 0, or 0 Kelvin. Okay, so that's kind of why we need to use the Kelvin temperature scale instead of even Celsius. So one of the things that sometimes problems you're working, Celsius is metric and Kelvin is metric. They're both metric. But your gases need to be in units of Kelvin temperature-wise. When you work gas problems, your temperature needs to be in units of Kelvin. So the way this might be something handy to put on your note card that you're going to come take to your final exam. Remember, there will be gas problems on your final. So if you are given, for instance, Celsius temperature, okay, it's metric, right? But you need the Kelvin temperature because you're dealing with gases, okay? This is what you do. You add 273.15 units to it. That's probably the most likely scenario. Okay, if you are given the Kelvin temperature and you want to back it into Celsius, what you got to do is subtract 273.15 units, and then that will give you the Celsius temperature. Notice one of the things, and we've done a lot with factor label problems and ratio, using an equality as a conversion factor to go back and forth between different units. For this temperature scale, they're just offset by 273.15 units. So I said a minute ago that as long as your gas is behaving ideally, you don't care if it's nitrogen, oxygen, carbon dioxide, carbon monoxide, argon gas, you get the idea, okay? But if it's behaving ideally, these two assumptions are followed. First off, and again, I won't draw the box again, but the box I drew this morning had those little particles confined to that particular box, ramming around. Excuse me. One of the things we know about gases is they go very fast. They have the most kinetic energy compared to liquids and solids. So those gas particles need to basically be independent of each other. There are what we say no intermolecular forces. They don't care that the other gas particle is there. Okay, so that's one assumption. And the other assumption is kind of weird. You know how we said, I think we started out maybe clear in Unit 1, we were talking about matter. We said all matter has mass and occupies space. Well, here you go. If the gas is behaving ideally, basically we said it has no space. It occupies no space. That's to say, relative to that container you confined it to, the volume of that gas particle is negligible, 0, which is kind of weird. So here's the deal, and I can't remember if I put it in my slides or not. If you, for instance, are working at high temperatures, okay, the first one works real well. Basically, if you're at such a high temperature, they have all that kinetic energy, they're definitely not going to stick to each other, okay? The bottom one, it works real well at low pressures. What a low pressure means is basically you have a big old box that you're allowing those gas particles to run around in. So if you have a big enough box, then yeah, the space that your gas particle occupies is basically 0 compared to the box that you have it in. So that's kind of how those go. Oh, I did have it. So in italics. But you know what? Have you ever heard this before? You know what assumptions, what's the first part of assumption? Or actually, I know it's even worse than that. You could take the word assumption and divide it up into makes an ass out of you and me. You know, have you ever heard that before? Watch out for assumptions. Hey, I didn't come up with that. Somebody else did. Okay, so I guess I do go on to kind of finish up this part talking about gases and ideal gas law behavior. So in the next part, we are going to introduce something, actually it's on the next slide, I guess, something called the ideal gas law equation. And a lot of times we don't really think much when we think it's this gas equation that relates those 4 things that I said, the pressure, the volume, the temperature, and the number of moles. But the ideal gas law equation assumes this ideal gas behavior. So that's the one for low pressure. Okay, oops. Okay. So the ideal gas law, or ideal gas law equation, to me it reminds me of almost like a physics equation. I would put this one on your study sheet too. The thing that reminds me about a physics equation is it's kind of what I call a plug and chug. Okay, so if this is my this is my box. Okay, and these are my gas particles. Okay, and I told you the 4 things: pressure, volume, temperature, and remember it's number of moles. Basically, the way you work gas problems is you'll be given, let's just say you're given the first 3 and you have to come up with moles. Okay, so my point is you're given 3 of those 4 things and you have to knock out the other thing. Now, here soon in part 2, I'm going to explain what R is. But you know what P is the pressure of the gas, V is the volume you're confining it to, N is the number of moles of gas, and then T is the temperature. So let's go on to part 2 and keep talking about gases. So I fuss because they're guys, right? There's Boyle's, that's his last name. These are all dealing with gases. There's these laws, and I fuss because they're guys. And the other thing I fuss is like, duh. I mean, they just make sense. Boyle's law will talk about pressure and volume. Pressure and volume. Okay? And I didn't bring my little balloon here, but remember that if you blow up a balloon and it has a certain volume, and you're like, okay, so those little gas particles are great with that. And if you decrease the volume, the pressure increases. Okay? So actually, those two we talked on Friday, that they have what we call an inverse relationship. I said if you decrease the volume, the pressure will increase. That's what we call an inverse relationship. And I'll go ahead and kind of show you how we wrote that. We said that pressure is proportional to 1 over V. Okay? That's how we wrote that. That's Boyle's law. And we're going to kind of reinforce that, building up to the ideal gas law equation. And then Charles' law, that's another duh, right? It's temperature and volume. Temperature and volume. Okay, this is the one where I said you buy a balloon at Hy-Vee and it's not really inflated to what you hoped it would be, but when you put it in your warm car, the temperature goes up and it gets tighter, it gets larger. So increased temperature, increased volume. Okay, if your volume is allowed to swell, it will. Okay, so those are directly proportional. So as one goes up, the other goes up, which is different than the other. And so we said that actually temperature is proportional to volume. And Avogadro's law, I mean, these just make sense, right?
Oh no, he has a law too.
He does have a law, which it makes sense. Remember, Avogadro's number is the number of particles in a mole. So the dude's all about moles, and so actually that's what he did here. It relates moles and volume. Okay? So that's kind of like if you're blowing up a balloon, you're putting more moles in your balloon. So you're increasing your N, and it increases your volume. It has to increase your volume as long as your pressure is going to be the same. So actually, these both are what we call directly related. So here in a minute, we're going to see N is proportional to V. That is Avogadro's law. And then we're actually going to combine all those and get your PV is equal to nRT, the last slide. We're going to combine all those. So we'll have some pictures to kind of, convince us that if you take any two variables of those four, we can kind of almost intuitively know how they're going to behave. So Boyle's law is all about volume and pressure. And so if you have, as one goes up, the other goes down, and we call that an inverse relationship. And we can use the proportionality symbol just like this, though. Okay? So here's one thing I didn't show you Friday. I don't think I did. If you want to replace that proportionality symbol, like infinity with a byte taken out of it, with an equal sign, we can do that, but we just need to introduce a constant. Okay? So here we go. It's going to have an equal sign there instead of the proportionality symbol, and we're going to introduce the constant variable k. Okay. Now, gas law problems are kind of, let's see, how do I say this? A little algebra intensive. Let me show you how we got from here to here. Okay. So we could say that, make sure I get this right. Volume is equal to 1 over P times K, right? So I don't have a proportionality symbol, I have an equal sign, and I throw in the letter K. Now, I don't know, I'm not an algebra teacher, okay? But let me show you when I think about that what I think of. But we have kind of talked about this. I think of this as this. V is equal to, I'm going to put that in the numerator. V is equal to K over P. You guys buy that? V is equal to K over P. Right? The last thing I'm going to do to get it to that form is what I call crisscross. Actually, I'm going to rewrite this down here. Do you guys buy this? V over 1 is the same thing as V is equal to K over P. Okay, so here's my crisscross. So I can, and I call it crisscross slash flatten out. I can flatten that thing out by basically crisscrossing. Okay, I can write V times P is equal to K times 1. VP is equal to K. And if you want to get really technical, I can move these two around, can't I? So PV is equal to K. Now, I won't belabor that like all the time, but that's kind of how that works. So start to begin kind of thinking about algebra. So that's Boyle's law. And do you see how this is pretty neat? The way this works is those multiplied by each other needs to be constant. Okay? So doesn't this make sense? If your P gets bigger, your V needs to get smaller in order for it to be a constant. Or if your V gets bigger, your P needs to get smaller. So that's how that works. That's Boyle's law. So I think I've got a bunch of pictures to talk about Boyle's law again. And sometimes it's about finding the gas of interest. So in your lab on Thursday, I'm excited you're going to do some like little gas experiments. But can you guys see that the gas of interest here is right there? Oh boy, that didn't show up very good. Let's do this. That doesn't show up very good. How about this? Okay, so the gas of interest is in that chamber. So clearly, as you decrease the volume, you increase the pressure. Here's another one for you. This is liquid mercury. This isn't a mercury barometer, but the gas of interest is right there. Is that not adorable? Okay, and we know what the pressure of that gas is related to this height of the liquid mercury. So what if we put more liquid mercury in that column? It's open kind of on the right there. If we put more liquid mercury, it squishes it down. Okay, so now your new volume is right here, okay, instead of right here. Again, it's kind of like the tire pump. We decrease the volume, and actually that's kind of a function of increasing the pressure. The pressure that that volume of gas is experiencing is related to the height of that liquid mercury. So this is actually to kind of look at pressure versus volume. Okay, so again, we decrease the volume. As we decrease the volume, okay, we increase the pressure. Here's another one. And I think we looked at this before, kind of a movable piston. So the pressure that's being maintained, the pressure of those gas particles in that chamber, actually, there's two things to kind of show you the pressure. There's that weight, excuse me, on that movable piston, and then we have this cute little pressure gauge out to the side. So let's just say we put more weight on it, a bigger weight on it. Of course, that movable piston goes down. Okay, again, we decrease volume and we increase pressure. And then we have this one. I think this is kind of fun. It's like, really? So the gas of interest, again, is here. I don't know if you guys can see. This is the end of the syringe plunger. Okay, so there's your gas of interest. Now, you guys have used Erlenmeyer flasks. I think you guys used them in your last experiment in the lab with your sodium bicarbonate. Well, this is an Erlenmeyer flask with a side arm, so, okay, it's fancy. The other thing about these Erlenmeyer flasks is they have thick walls, and the reason they have thick walls is so you can actually pressurize them. They're a thick-walled, side-arm Erlenmeyer flask. All right, so you see the gas of interest, you kind of got the idea there. So now, between the two, this Erlenmeyer flask now has a stopper on the top. And what they're saying is basically you have attached this to a tire pump and you are adding air. Okay, now that's not our air of interest. What we're doing is we're adding air is we are increasing the pressure here, increasing pressure in that chamber, which then actually makes this go down. Increasing pressure makes your plunger go down. If you were to go back, okay, and compare this volume with the previous one, that volume is decreased. Increased pressure, decreased volume. Again, just a little bit more. Okay, this even has less. Increased pressure, decreased volume. But we're not done with this one. Okay, with the setup. These marshmallows minding their own business. So this is hopefully kind of the typical size of the volume of a large marshmallow. So here's the deal. Those marshmallows are basically, they have a lot of, they are aerated. They have a lot of gas particles in them. So now instead of, now we're going to, again, on the next slide, you're going to see basically what happens to this poor little marshmallows when you add air. Well, if you add air, I guess I hadn't thought about this. Basically, what are you doing? You're increasing N, okay? Increasing the number of moles, and that's going to increase the pressure in here. And let's see what happens to, we increase pressure, you're supposed to decrease volume. Oh, I did it wrong. I thought I did it wrong. There you go. That's what you get when you take a tire pump. Okay, I know, poor little marshmallows. Okay, but let's go back to this one. I forgot this one was in here. Don't they look bigger? Okay, instead of a tire pump, check this out. This is awesome. Sometimes you need to actually draw a vacuum, kind of like your vacuum cleaner. And so actually that is decreasing N, okay? And if you're decreasing N, then you are going to lower pressure. And as you lower pressure, as pressure goes down, volume should increase. And that's exactly what you're seeing there. Is that not cool or what? So yeah, kind of got ahead of myself. And we're almost done with Boyle's Law examples. This one, again, a movable syringe. It's kind of a nice little setup. The gas of interest is here, right there. And what you're going to see is basically they're going to add lead shot to that top there. So that's actually going to increase the pressure, and hopefully we should see that volume decrease. This one's good because actually they plot it on this graph. So with no shot in it, they're actually showing you not volume, but 1 over volume. So now, if this actually is going to, this mass that we're going to put up here is a function of, or relates to the pressure. Okay, as we increase pressure, we should see the volume decrease, but here's the deal. You should see, as you increase pressure, you should see the volume will decrease, but check this out. 1 over the volume will increase. And so that's actually what you're going to see here. 1 over the volume will increase. Okay, so add shot, the plunger goes down, the volume's less, but 1 over the volume is more. Less is more. Okay, more shot, 1 over the volume is even more. More shot, 1 over the volume is even more. Okay. I don't have as many examples for Charles' Law, but let's take a look. So we said, and I thought we said this on Friday too, if you're just looking at volume and temperature, if you increase the temperature, the volume will increase, okay? If you're going to keep the same pressure, you better give them a larger room to run around in. So let's go ahead and introduce a constant. We're going to put an equal sign there instead of the proportionality symbol, and we need to introduce a constant. So what you're going to see here in a minute, if we do what we did a minute ago, this would be V is equal to T times K, right? So if we want to get K by itself, I'll change my colors here. We know that we can divide both sides by T, okay? And then that simplifies to V over T is equal to K, because these two T's cancel out. That's kind of algebra, right? And that's exactly what this says. V over T is equal to K. So that's Charles' law. So I do have an example to show you with balloons here. So in here, the gas, of course, let's pick on this orange balloon. The gas of interest is right there, okay? So that has a particular volume. Now, with all of these, we're assuming that the other two variables, if we're messing with volume and temperature, the other two variables would be what? Pressure and number of moles. We're assuming that the pressure and number of moles stays the same. That middle thing, thou shalt not play with liquid nitrogen, right? Okay? But, let's see, is it liquid nitrogen? Yes, it is. But that is very cold. N2 liquid. So here's the deal. Can you see where if we were to find the orange balloon, it looks like there, okay, maybe that the volume is much less. Okay, basically we lowered the temperature, and that means that the volume also went down. Lower the temperature, lower the volume. And then just to show you that nothing was harmed, you know, this is like many this is like many processes. This isn't a chemical reaction, but like many processes, it can be undone. So over here, this last one, then as we increase the temperature, we brought it back out, it's going to increase the volume. So it's pretty clever. Another practical example of increasing temperature, increasing volume is a hot air balloon. Okay, so hot air balloons work by having basically a nice little flamey thing here. I'll put flame, but I know it's much more complicated than that. So basically what it's counting on is adjusting this temperature of that gas that's in the balloon. So as you increase the temperature, it increases the volume, and it gives it a different density, and so it can be buoyant relative to the air it's around. Okay, so here's where I get to tell you, or try to show you, why when you're working gas law problems, why that temperature cannot be in units of Celsius. Celsius are a great metric unit, okay? But it has to be in units of Kelvin. So if you go back to the liquid nitrogen, okay, that balloon that somebody blew up and they put it in liquid nitrogen, it almost looked like the balloon had zero volume, okay? But actually a gas literally will have a volume until its temperature is absolute zero. So what this is doing is gonna, and I have another slide coming up to show you. Basically, think of it this way. This is taking a particular volume and cooling it down. Okay? Okay, so as we cool it down, the volume gets less and less and less and less and less and less, okay, until we get to that critical temperature of negative 273.15 degrees Celsius. And that is equal to 0 Kelvin. That's absolute zero. So that's why I think of it that way. When you work gas law problems, it needs to be in units of Kelvin, not Celsius. So what this is kind of showing you a pair of temperatures, a pair of temperatures. That temperature in black is the Celsius temperature. That temperature in blue is the Kelvin temperature. And they're all offset by 273. So we said if you were given Celsius and you want to get to Kelvin, what you do is you subtract 273. So like, you add 273, sorry. Final answer. Okay, there. Okay, so if you take the black number and add 273, okay, 100 plus 273 is 373. 0 plus 273 is 273. Negative 100 plus 273 is 173. You get the idea. And this actually is picking on the gas helium, but like I said, if the gas is behaving ideally, we don't care if that's nitrogen gas, helium gas, carbon dioxide, water vapor. It's all going to follow the same pattern. And it's showing you as you cool it down, okay, it's showing the volume decrease. That's Charles' law. And I'm not going to show you this video for two reasons. One is I'm not sure it's going to play. But two is I think we've kind of hit this one pretty good. That's the word imperative. So my thing is on your test, if you see PV is equal, if you need to use this equation, okay, your units of temperature must be in Kelvin, not degrees Celsius. And like we saw a minute ago, if you have degrees Celsius, all you need to do is add 273 to get your Kelvin. That's it. All right. So one thing we didn't look at yet is Avogadro's law. So Avogadro, yep, he's famous for 1 mole is equal to 6.022 times 10 to the 23rd particles. Okay. So these are, if you increase the number of moles, like you're blowing up a balloon, your volume's going to increase. And if we want to replace that proportionality symbol with an equal sign, we can, but we're going to end up with kind of like we ended up with pressure, kind of like we ended up with volume and temperature. Okay, we're going to end up with volume over number of moles, and it's equal to that constant K. Avogadro's. Let's see. No, we want to. Okay. So, here we go. No K's, right? Just back to proportional. Okay. We said that volume and number of moles are proportional. As one goes up, the other goes up. We said volume and temperature is proportional. As one goes up, the other goes up. We said volume and pressure had kind of that upside down or inverse relationship. As one goes up, the other goes down. Now here's one for you. We can basically combine all of these, they're lined up this way on purpose, to make this. So all we did is basically say, if volume in each of those cases is proportional to this, then volume is proportional to basically N times T, okay, N times T divided by P. Well, you know where we're going with this. We're going to get rid of that proportionality symbol and replace it with an equal sign. So let's go ahead and do that. So V is equal to NTK over P. I'm going to go ahead and do my magic here. I'm going to put V over 1 so that I can flatten it out with confidence. So as I flatten it out with confidence, basically I'm going to have V times P is equal to N times T times K. Okay, I know that looks like a U, but really it's a V. Let me go ahead and rewrite this. I'm going to turn these two guys around. I'm going to say PV is equal to NKT. And here we end up with, I don't know if you had to fill all those in. PV is equal to NKT is really PV is equal to NR. So our K basically has been gone up a notch. Instead of some generic letter K, we're actually going to introduce something that's important to gases called the ideal gas law constant, R. And this is the last slide in part 1. Yeah, I kind of skipped a few slides. Skipped over a few slides. Did you guys all find this one? Okay.
Bottom of 5.
Bottom of 5, thank you. Perfect. All right. So PV is equal to nRT. So that's the one that we ended with part 1, and that's the one I would put on your sheet that you're going to take to your final with you. So in here, we've talked about units are very important. Units and dimensions are the same thing. So this needs to make sense with regard to things that are going to cancel and all that. So pressure will be, for our purposes, pressure will be in units of atmospheres. I know you guys, for the homework you handed in today, kind of did some going back and forth between like millimeters of mercury and atmospheres and all that. But we're going to focus on units of atmospheres for pressure. Volumes are going to be in the SI system, the liters. Volume's going to be liters. Excuse me. N is going to be number of moles in units of moles. And we already talked about the temperature needs to be in units of Kelvin. So here's the deal then. That value of R, because you set in stone the P, V, and the N and the T, the value of R, in order for your problems to work out, will have units of liters, atmospheres, per, that means it's in the denominator, mole, Kelvin. Now, if you kind of dabble in gas law problems, there are other values of R out there. Okay, there are other values of R out there. And those other values of R are not different because it's like a different universe and gases are behaving differently. Those values of R out there are different because they have different units. Okay, so we're going to use this value of R. And this number for R, 0.082058, okay, the number is important too. A lot of times on your final exam, I'll give you that value for R. But it's 0.082058 liters atmospheres per mole Kelvin. I just think of the cartoon Kelvin. Okay. So let's go ahead and do a problem. And like I said, they seem kind of like chug and plug to me. Sometimes, especially if it's been a while since I've done these problems, I like to draw a picture, you know, just to kind of get my bearings. I'll draw a P is equal to V is equal to, and then I'll keep it in, and the PV equals nRT, so I'll say N is equal to, and T is equal to. And I'll know 3 of these things, but you're supposed to find the 4th. So right off the bat, it says, what is the gas pressure? So under pressure, I'm going to put question mark. Okay. The next bit of information looks like a volume to me, 750 milliliters. Looks like they're giving me moles. That's the N, 0.0284 moles. The temperature, looks like I got a little bit of fixing to do, don't I? The temperature is 22.0 degrees Celsius. Sometimes when I'm kind of doodling the problem like this, I will go ahead and say plus 273 is equal to whatever the Kelvin temperature is, because that's a flag to me. And I'm ultimately going to use PV is equal to nRT. Okay, so basically this is going to be our question mark. That's kind of what we got going here. We know volume, we know N, we know R, and we know T. Let's go ahead, and while I have that doodle up there, do you see where if I was going to, P is what I'm after, I bet you guys buy this. If I divide both sides by V, okay, look what I get. I get P is equal to nRT over V. And actually, then I'm ready just to plug. On your final exam, remember you're going to have two sections. The first section is going to be multiple choice, and the last section is going to be work the problems. You're going to have to, when you work the problems, make sure that you show all work and use units. So here we go. I'll probably give this to you on your final, but this is the ideal gas law constant. In this universe, that ties PV and NT if the gas is behaving ideally. All right. So we need a little bit of fixing up. Okay. We know that we need to get the Celsius temperature in kelvins, but actually we had another thing to fix, and that was the volume. It was in milliliters, so we've got to get it to liters. So we'll fix that too, and then plug in. All right. So here we go. PV is equal to nRT. Almost sounds like a rap song. Okay, rearranging it for P because that's what we're trying to find. Kind of showed you we can divide both sides by V and get P is equal to nRT over V. So N is equal to that 0.0284 moles. That's from the problem. R is 0.082058 liters atmospheres per mole Kelvin. Temperature, we decided we need to take that Celsius temperature, 22.0, and add 273. A better number to add is 273.15. But notice when we do that, which is great, since we're adding, we round to 1 decimal. Okay, so that's going to be our Celsius temperature. And then our volume, we need to fix 2. And I guess, I can't remember where it's, but you know what we're going to do there is one of the things that you guys have been doing. We're going to put 1 liter over 1,000 milliliters. So that's our volume term. Ready to plug and chug. You know, I just think it's so pretty. If you choose to kind of write them out like this, you can almost kind of see where, you know, R is going to go there, and we're going to make sure we have our units. T is going to go there. V is going to go there. Well, here we go. So in the numerator, we have 3 terms. The first one is 0.0284 moles. And I probably would put that over 1. And the reason is because the R term has units in the numerator and the denominator. The middle term, R, 0.082058 liters atmospheres per mole Kelvin. And the third term I would probably put over 1 also, that 295.2 Kelvin. And then all we got in the bottom is that 0.750 liters. So if we look at units that have canceled, like I said, I usually put this over 1. Okay, I put this over 1. Because then I can see that moles will cancel. Kelvin will cancel. Actually, liters in the numerator will cancel with liters in the numerator of the denominator. So liters have canceled. And we're left with units of atmospheres. So when we go to write our answer, it looks to me like we have 3 sig figs there. We actually have 5 sig figs in the value of R we're using, 4 sig figs in the temperature, again 3 sig figs in the volume, so it looks like 3 sig figs. Did you get 0.917 atmospheres? Okay. So there won't be any homework assigned. When we come in on Wednesday, though, right off the bat, I'm going to, for credit, for 10 extra credit points, I'm going to give you a gas law problem, and you guys can knock it out. Okay? That's the plan, man.